Let us begin with our notes. So, you may have trouble seeing this because of the lighting, the mood lighting that I have going here. Don't worry, I have included a PDF in the Google Classroom stream here that is a scanned version of this, so you'll be able to see it clearly. You could copy these notes down either before you watch the rest of this video, or possibly after. It doesn't matter, whatever you prefer. But what we're going to do is go through Maxwell's 4 equations. There are 4 of them. And all we're going to be concentrating on is the meaning of Maxwell's equations. To apply Maxwell's equations in their full form and calculate and solve problems with them is something that you would have to be in high-level physics, college physics, possibly even grad school. It is an incredibly complicated topic. But what we're going to do is the AP has us just learning what the concepts are, and all you're going to have to do, be required to do, is to look at the equation and state what it means. That's it. Write out sentences of its meaning. And you already know enough math to be able to do that. The first here is what you might recognize as Gauss's law. So Maxwell, yes, he took laws that were already established, and then he took them a step further. You'll see his contribution. He contributed one little piece, and it may seem like a little piece, but it changed all of human history. It was a little piece that created something of enormous consequence, and it basically ushered in the modern era. James Clerk Maxwell ushered in the modern era. Cell phones, TV, electricity, light. What is light? Beyond that, what are all these technological things? Maxwell answered those questions. Before they even existed, he made it possible with his theory for us to be able to create radar, radio waves, TV waves, and now your cell phone signals going from one place to another. So here's Gauss's law, the first equation, and you see it stated in the familiar form with a closed integral EdA equals Q enclosed over epsilon 0. And right here I have something else I'll explain in a minute, but basically the meaning is this. We know that integral with a circle around it means that it's a 3D integral over an area that encloses, like a box or a coffee can, blocks off a volume from the rest of space. And so you integrate the electric field that's coming into or out of that area, and the answer is Q enclosed over epsilon 0. So electric flux into or out of a 3D surface is caused by net charge enclosed in a surface. So that's the meaning here. The net electric flux into or out of a closed 3D surface is equal to the net charge enclosed divided by epsilon 0. All you have to be able to do on the AP test is read that from the math over here. I have a little diagram here of a box, and if we have more electric field coming in this side, the back side, which we cannot see, then we have coming out, we have a net negative flux. And that means that we must have a negative charge enclosed in the box, a net negative charge. This here is how Maxwell's equations is stated in more sophisticated form. This is a very simple high school physics kind of form. This is what you would see even when you start studying Calc 3 in college. This triangle means a special kind of derivative, a derivative that is applied in 3 dimensions. And more so, what it means with being a dot product with electric field, it means that you're looking at how the electric field, or any vector, changes when you step in the direction of the vector itself. And to illustrate what that means, I have a little vector diagram here. So here we have a vector diagram. You can see that if I move sideways, perpendicular to the direction that the vector goes, the electric field in this instance, that the vector does not change. But if I move forward with the vector, you see the arrows getting longer, the field is increasing. That's what's meant by this. It's called the divergence of a vector. If it asks, how does x change when you step in the x direction? Here we would see a positive change. Okay. And also it's 3D, so it asks how the y vectors are changing when you step in y and how the z vectors are changing when you step in z. And so you can kind of see the spirit of Gauss's law here. If I make a Gaussian box like this, you see going in here, I have less electric field than I have coming out of my Gaussian box. And so I must have a Q enclosed positive here. So this idea of a field increasing when you step with it is basically what we have, the same idea with Gauss's law, that the flux into or out of a box is captured by that kind of derivative. So that's Maxwell's equation. Again, you don't need to know this. I'm just putting it there because I think it's interesting and I think it's really cool. And also, you'll see it soon enough in college, okay? The second equation, okay? Let me move this up. Okay, let's see if that stays. Okay, how are we doing? A little higher. Okay, so you see that we basically have Gauss's law, but with the magnetic field. So it's Gauss's law on the left side, B instead of E. So magnetic field integrated over a 3D closed box, that's what the circling integral means, it always equals 0. Okay? So here's the meaning. Again, you read what you see here. If you draw any 3D closed surface anywhere in the universe, the flux in, the magnetic flux in, has to equal the magnetic flux out because the net flux is 0. And here's a little diagram indicating or illustrating that effect. This is the magnetic field around a bar magnet. And you might say, well, if I draw a Gaussian surface right at the North Pole, don't I have magnetic field lines coming out of the surface? Don't I have this being positive? Well, if you look at this side, inside the magnetic field lines are actually coming in this side of the surface and going out that side of the surface. I have 3 magnetic field lines going in, 3 going out, net flux is 0. Here's another example, a wire, current coming straight at you. Creates a magnetic field by the right-hand rule going around like this. If I draw a 3D surface here, you see I have 2 magnetic field lines coming in, negative flux. 2 coming out, positive flux, net flux 0. Another interpretation of this equation is that magnetic monopoles do not exist. You can never have just a north pole all by itself, because then if we created a 3D Gaussian surface around it, we would have net magnetic flux coming out of that box or that surface or whatever it is. So you must always have a north and south pole of equal strengths. Okay? Is that always true? It turns out we've never found a magnetic monopole anywhere. Doesn't mean it can't happen. Maybe someday someone will discover it and we'll have to rework Maxwell's equations. But for over 150 years, this has been true. Okay, so that's the second law. Gauss's law, second equation, Gauss's law for magnetic field 0 all the time, not Q enclosed over epsilon 0. The third of Maxwell's equations. Let's see, okay, we got it here. The third of Maxwell's equations is basically Faraday's law. We have electric field integrated around ds, s instead of dA being area. ds is an arc length. So what you're doing is integrating around a line, not a surface, and it has to be a closed line. In other words, the line has to make like a circle or a square, a rectangle. It has to close in on itself. It has to be a closed line. Okay? So the electric field integrated around that closed line is equal to the change in flux, magnetic flux, over time. Faraday's law, change in magnetic flux per time, with the minus sign there, of course, is the electric field integrated around the surface's edge. And as we know, the electric field integrated around a path is voltage. So we wrote Faraday's law as mth equals negative d flux dt. Okay? But that's basically it. It's Faraday's law. So here's what you have to be able to do on the AP. The meaning, a changing magnetic flux through a two-dimensional surface causes an electric field along the closed path that forms the boundary of the surface. So you know this well. We just basically finished up with electromagnetism, or we're working on finishing up with it, but we finished all the topics. Faraday's law. And so here I have an example. I have a magnetic field coming through this loop. When B decreases, remember we have to have a B induced to try and keep that magnetic field coming out constant, so we have a B induced going this way. And my thumb tells me the direction of the current induced if this were a wire. And so if the current's going this way, the electric field's going around. So see, that electric field is caused by the changing magnetic field inside. And that's the concept here. This is now the sophisticated way to write this concept. This is that same derivative, three-dimensional, but with a cross product. So derivative in x, derivative in y, derivative in z, but crossed with the electric field. And what a cross product is, remember when we did QVB sine theta, it's all about 90 degrees. So a velocity and magnetic field had to be 90 degrees to each other. And so what we're applying is a derivative, but 90 degrees to the direction of the vector. So I can have I'll show you a field here that has this is, by the way, called a curl instead of the other one called a divergence. This is called a curl. And here, this vector field has a divergence of 0. In other words, if we step in the x direction along any line, we have a constant electric field. Here, we've got a longer electric field here, but as we step in direction x vector doesn't change. Divergence is 0, but the curl is not. And what that means is that if we face this way, so I'm facing this way, and I step sideways, the curl asks what is happening to the electric field in the forward direction as you step sideways. The derivative at a 90 degree to what the vector is. So you move 90 degrees to the vector and asks, is that vector changing? And this shows it is. As I step in the y direction, well, I guess I could step in the positive y direction, I see that the forward x vector is decreasing. This would have a negative curl. But it happens in 3D. So you have to step in the z direction, step in the y direction, and look at what the perpendicular vectors are doing as you do. So it's very complicated, but that's the most basic concept of what the curl is. And you can see that if we create a loop around here, that when we come around and integrate the electric field, that as we come this way, we have more electric field going this way. When we come around and integrate this way, we're going to have less negative electric field because we're integrating this way and the electric field is this way. So we're going to end up with positive integral of electric field if we go around this way. So you could kind of see the concepts of these two linked together if you draw a loop. The way to prove that, I forget, I think it's called Stokes' theorem in Calc 3. You'll have to prove that these two things are equivalent to each other. But again, not necessary. I'm throwing things out because I just think they're very interesting and to sort of maybe put some ideas, some seeds into your mind for the future. All you need to be able to do is take this and come up with these words. You would literally be writing out an explanation in sentences on the AP if they asked you a Maxwell's equation question. So far, nothing new. 3 equations. And we can recognize all of them as things that we had already studied. Now comes the 4th, which includes Maxwell's contribution. So let's see, I got that, there we go. So here it is. BDS integrated around equals mu zero I enclosed. And right there, without that piece, you can recognize Ampere's law. And so this is the piece that Maxwell added in 1860. Little thing with huge implications, huge applications. Okay? But let's talk about first what it means. The meaning. Again, you just read this as best you can with the math that you know. So the magnetic field around a closed loop is caused by two things. We used to say it used to be you make an Amperian loop, and if there's current coming through, it's going to create magnetic field around that Amperian loop. That's that part, the I going through. But something else creates the magnetic field. Mu zero, epsilon zero, constants we could recognize, times the derivative of the electric flux, not magnetic flux, with respect to time. So the magnetic field around a closed loop is caused by the current and or, not just the current, but a changing electric flux through the surface bounded by the loop. I'm just reading this out, right? That's what it says. The magnetic field around is caused by caused by I enclosed and changing electric flux. That's all you need to do for the AP. This is it expressed in more sophisticated manner. The curl of the magnetic field. Again, this BDS instead of EDS like we had in the previous one. BDS is the curl of magnetic field. How does it change in the forward direction as you step sideways? It's caused by current density and changing electric field with respect to time. That's the new piece, okay? Now, before I go on with that, with the implications behind it, I just want to show you how Maxwell thought of it. So this is his little demonstration, okay? So a visual. I've got a battery here, a resistor here, a capacitor here. And when I connect this circuit, current's going to be flowing this way. And so if I make an Amperian loop here, I have the wire enclosed. And then I, with the right-hand rule, I see the magnetic field is going to go around this Amperian loop, and I could figure out as mu 0 I over 2 pi r, right? All that, right? But then, if I make an Amperian loop inside the capacitor, then, if you leave off that piece about the changing electric flux, there is no I enclosed inside there, right? Because the capacitor stops the current. You have charge building up here, charge building up there. No current flowing through the gap of the capacitor, which is just air or a vacuum. So without that changing electric flux, the magnetic field integrated around that path should be zero. That would violate the principle itself, because if there was magnetic field zero, and then I sidestepped here, I would go from a place of magnetic field forward coming out of the paper. I step sideways and suddenly there would be no magnetic field. There would be a change. And so that means that there would have to be an I enclosed in an Amperian loop up here. And Maxwell said there's no I enclosed, so there cannot be a change in magnetic field. The magnetic field here has to be the same as over here. So if there's no I enclosed, what's going through that loop? As the current's coming here, more and more charge is building up here, positive. More and more charge, negative, is building up here. So the electric field is growing through that loop. And that's how he reasoned out that the changing electric flux, not the current, there is no current there, but there's a changing electric flux, that must create B. Over here, current creates B, right? So we have the BDS, mu 0 I enclosed. Over here, BDS is the mu 0 epsilon 0, the change in electric flux part. And so the same magnetic field along. That's how he put together That's how he thought of that piece. And so the last thing I want to talk about is what the implication of that is. If you look here, it's not just current density that causes magnetic field. Changing electric field creates magnetic field. And if the electric field changes with a double derivative, when you take the derivative with respect to time here, it'll create a magnetic field that's changing. So changing electric field creates a changing magnetic field. What does a changing magnetic field do? We go to Maxwell's equation 3. A changing magnetic field creates another changing electric field. So what now does this changing magnetic field that creates a changing electric field, what does that changing electric field do? A changing electric field creates a changing magnetic field. What does the changing magnetic field do? It creates a changing electric field. And that's what he discovered. If you wiggle the electric field or the magnetic field, you create waves, wiggling electric and magnetic fields coexisting, and one produces the other. So we have an electric field makes a magnetic field, creates an electric field, creates a magnetic field, and that's an electromagnetic wave. And he discovered that was light. So remember the shirt I wore at the start of the year? It said, God said, and then he had all these equations, Maxwell's equations written out. And then at the bottom it said, and then there was light. You know, that was the little play, little joke thing that they created. But that's really what light is. It's complete consequence of Maxwell's equations. Very beautiful stuff. Now again, as I said, because people now understood how light was created, they were able to just wiggle at different frequencies and shake the electric and magnetic fields faster or slower. And basically, if you shake slower than visible light, you make microwaves, like the things in your oven that cook the food. But also, your cell phone uses microwaves. So your cell phone is shaking electric and magnetic fields in such a way that those vibrations of electric magnetic field go through space and get to the tower and give the signal. The tower makes its own shaking electric and magnetic field. They go back to your cell phone, and you have a back and forth, and you could text your friends, call your friends, download videos, whatever. All again because of James Clerk Maxwell in the 1860s.